Bismillahirrahmanirrahim. Today we'll talk about Pushdown Automata PDA and we'll also talk about the Chomsky normal form. Previously, we have seen what is basically the context-free grammar. So, a language that is defined by a context-free is known as a context-free grammar. Context-free grammar is a subset of the context-sensitive grammar. As we already discussed previously, we have regular language, then we have context-free grammar or languages, then we have something which is known as context sensitive languages, and then we have something which is known as recursively enumerable languages. So that's why you can see here it is written that the context free grammar are the subset of what subset of the context sensitive grammar. Context free grammar is defined by V input, P and S. Okay, so V is basically what? V is the finite set of the variable. Variable means non-terminal. Keep in mind it should be non-empty and it is represented by a capital letter. However, this is represented by these are the set of finite alphabets. These are known as terminal. They are also non-empty. They are represented by lowercase. It might be letter, it might be digit, it might be any symbol. Here it is written that the intersection of V and sigma is empty. Why? Because the same thing cannot be used for the terminal as well as the non-terminal. It means it is impossible to have any item that falls in both category, which is basically an input as which is actually a terminal and non-terminal. So that's why their intersection is empty. P is basically what? P is a set of production rules which is in the form of this implies alpha implies beta. Alpha is basically the left hand side, beta is the right hand side. On the left hand side, you will always be having one variable or non-terminal. However, on the right hand side, it is basically a combination of what? It is a combination of the terminal and as well as the non-terminal. Any repetition in the previous lecture we have already discussed, it might be only terminal, it might be only non-terminal, it might be the combination of terminals and non-terminal, and we have something which is known as one of the terminal which is non-terminal, which is the start. Context free grammar, in case of context free grammar, always on this side what you will have a single variable or single non-terminal. Take an example. Let's assume we have this as a grammar. Within this grammar, we have the non-terminal, which is S and X. We have the terminals, which is A. However, this thing, the important point here is lambda, yani it doesn't comes under the terminal or non-terminal. It is basically what? It is basically a. And then we have what? We have the starting variable here is S, and these are basically the production rules. Now let's see what is push-down automata. If you remember previously, what we did in order to represent the regular language, what we use finite automata. Similarly, in order to represent the context-free languages, what we did, we use something which is known as push-down automata. So push-down automata is a way in order to implement the context-free grammar. Same is the case, the finite automata or DFA or NFA or epsilon NFA or transition graph. Basically, they are used for the regular grammar. So a DFA can remember a finite amount of information. That was basically a drawback of the DFA or the finite automata, that in that case, in that category, we don't have any memory that can hold the intermediate results or holding the variable. So that's why it has a finite amount of can only store finite amount of information or deal with a finite amount of information. However, in the case of PDA, it can remember an infinite amount of information because of what? Because of the stack. Pushdown automata is a finite automata, okay, but along with that, we have something which is known as the extra memory. So we cannot say that pushdown automata is only finite automata. It is basically a combination of the finite state machine, which is epsilon NFA. Along with that, there is a stack, a memory called a stack, which helps the pushdown automata to recognize the context-free languages. It is more powerful. Why it is more powerful? Because it has an additional thing, which is the stack. Here is an example of the stack. You know, inside the stack, this is the first element you input. This one is the second, this one third, fourth, and fifth. When you need to remove, you have to remove first the fifth element, then the fourth, then the three, then two, then one. So it is just like first in, last out, or last in, first out. Here it is actually in order to check the opening and closing of the brackets. So what we did, opening is the push, so it will be push, push, and then it will be one pop. Still the stack is not empty. If the stack is not empty, it means that the equation is not the balanced equation. Here, if you can see, there will be a push, then there will be a pop, and then there is another pop, but there is no element, which is, so it will give an error, which is underflow. So even here, the problem is that this particular equation, in this particular equation, the parentheses are not balanced. So push down automata is a new type of computational model. It has an NFA, but has, it is like an NFA, but has an extra component, which is like which is basically a stack. So the stack basically provides an additional memory beyond the finite amount available in the control unit. Inside the control unit, there is some small memory, but along with that, it actually provide an additional memory. The stack allow the push down automata to recognize the non-regular languages and as well, but that part of non-regular which belong to the context-free grammar. Push-down automata are equivalent in the power to the context-free grammar, because push-down automata is a way in order to implement the context-free grammar. A push-down can write a symbol on the stack and can read it back by using two operations. One is known as pushing, another one is known as removing or popping. Access to the stack, we know that even the reading and the writing in the stack is only at the top, and it is last in, first out. Same is the case finite. What is finite automata to the regular expression? Same is the case PDA with a context-free language. So PDA is just like epsilon NFA plus a stack. So here is basically the control unit. Here is the input, and here is the stack. And the outcome can be either that particular equation or that particular string belong to a language or not. So the outcome can either be accept or reject. A stack is valuable because it can hold an unlimited amount of information, but still, yani, we will see at the end in the stack, the problem is on one side you can do the insertion and you can do the deletion. So if I can see the component of the stack, it consists of the input tape, it consists of the control unit, and it consists of the stack with an infinite size. So same is the case when we design a as we design finite automata to regular language. Okay, so similarly, we will design PDA for the context-free grammar. So for the context-free grammar, lead to context-free language. This context-free language can be implemented using PDA. Regular grammar lead to regular language. This regular language can be defined by finite automata, any type DFA, NFA, epsilon, NFA. Regarding the PDA acceptance, there are two approaches for the acceptance of the string in the PDA. Either it will reach to the final state, or either the stack is empty. If we are representing it visually, so it will lead to the final state. And if we need to see the stack by itself, so even if the stack is empty, so it means that that particular string is accepted. In case of PDA, what we did, it consists of 7 tuples. It consists of, first of all, yani the same thing we did previously as well, the finite set of states. We have the final state as well as the initial state. We are already aware of these 3. The next thing is the input alphabets. We already know about the input alphabets, and we already know about the transition function as well. So the only thing that's a little bit different is this, which is a finite, stack symbols. What are the symbols that is inside the stack, which is represented by top? And here we have something which is known as Z0. Z0 indicates the element that is in the stack when it is empty. In some books, Z0 is used. In some references, even $sign is used. So now we will explore the transition function. The transition function consists of Q consists of A, consists of X, consists of B, consists of gamma. Now let's see what is Q. Q is basically a state, and a current state where you are. A is actually an input symbol. Okay, the input symbol, it can be either A, it can be either B. It is from the sigma. And if A is equal to empty, okay, if the value of A is empty, then it indicate, if A is is equal to this, okay, so it or lambda, it indicate, you know what it indicate, that it is empty. Or at the end, what we did, as we will discuss, at the end of every string we have this lambda or this empty symbol. So in that case, this, and it will indicate that this is the last character inside the string. So the other thing is, we have this X. X is basically a stack symbol that we have at that time when either you are doing insertion or deletion. It is basically from the member of what? From the member of this term. Now we will see the output is from this is a finite set of pair of this. P is the new state after performing that operation, and the gamma can be by these three. It can be either this empty, it can be either X, it can either indicate, for example, Y and Z. So if you want to, do popping, in that case, how it will be represented? If you see that you have, this empty symbol, if you see, for example, you want here it is X, and on this side also it is X. So it means what you did, you make a no change, because here it actually indicates the, after operation, the top two elements. So here what we did, Yani, if you want to do a push, so if X is equal to Y and you did a push, and previously inside the stack top it was Z, so it will indicate YZ. So YZ, so here it means it is push, here it is no change as it is, and having this empty symbol indicate that the operation that is performed is pop. So in the finite state machine, we have here A, here B. Okay, yani A is one state, B is another state, and this is basically the input. In the case of push down automata, we need on this edge three labels. One is basically a Q, which is the current state. A is basically the symbol that you have, you get in from the input tape, and X, the symbol that you are reading, and X is something that you have it currently on the top of the stack before performing any operation. Let's discuss one of the example of a PDA that can accept equal number of A's and B's. So it is A power n, B power n. This A power n, B power n is actually a non-regular language. It's not a regular language. Why? Because we need to keep the track of the value of n, which we cannot do by using the finite automata. So here what we did, as I told you, when you currently, for example, this is our stack. Inside the stack we have Z0. This just represents an empty symbol. In some books you will see even you have to add this empty symbol by yourself, and in some books or material it says that automatically we don't need to push that 0, we just need to start directly with the string. So here let's first make a push down automata for, in this case, as the the least string is A and B. Okay, so in this case what we did, we will say that if it is A, do a push, if it is B, do a pop. So first of all, inside the stack you have Z0. So here what we did, if we need to write a transition function, first of all we'd make a state which is Q0. Okay, so we are actually in Q0. The input we have, because this is, we want to actually make it for this, which is A, B. So the input we have is A. Inside the stack top, what we did, we have Z0. What we want to perform, we want to perform a push. As currently we are in the this is the first operation we did, so we need to be in the same state. We will be still in Q0, and here we will add a, so the topmost elements are a, z, 0. Keep in mind this sequence is very important. We cannot write z0 a. So it indicate what? It indicate that currently if you see this, so if you can see that here it says z0, it means the stack was empty. A is the first element that you have inserted. So what we did, we have yani function. This function can be written as here in transition diagram as a z0 and then a z0. We don't need to write the state because the state is already there. So what we did, we put a loop and we just wrote yani this one. Forget about this thing for now. Now, after that, when you read B, so still you are in Q0. Okay. Here the thing is, this was pushed, this is pop, as it is a different operation. So that's why I need to change the state. But okay, let's first write you are in Q0. The input you are getting is B. On the stack top, it is A. What we want you to do a pop. In order to do a pop, for this was pushed, so new operation, I need to move to another state, which is basically Q1. As it is pop, I just need to write this thing. So here on the diagram, I will write BA slash empty symbols. So you can see here. So we are in Q1. Okay. As I told you that whenever you have the string, at the end of every string, there is an empty symbol or a blank. So that's why after that, when it will read a blank, okay, so A is basically pop. When it read a blank, okay, and then we are in Q1 when it is blank, as this is like an acceptance operation, and on the stack top it is Z0. What you need to do is, you don't need to do anything, just move to another state, which is Q2, and keep Z0 as it is. Okay, so you can see it is empty symbol, Z0, key Z0. So for now, yani, remove even this one. For now, this actually fulfill the requirement of A, B. What if we have, yani, instead of having A, B, if we have more than one yani A's and more than one yani B's? So in that case, if you have A and B, B. So we already have one A. I need to write for another A. So this is also pushed. So it means that if I am in Q0, if an input is A, the stack top is A, what you need to do is, as this is pushed, you will be in the same state, which is Q0, and the top two elements will be AA. So this is the transition is, here you can see this basically define what this define that you have. If you want to again do it, halas, this will be executed. Now for the B, okay, first B, it will pop this. For the second B, we don't have. What we did, we only here define another loop. So here, this is basically you're growing the stack. This is also popping the stack. You are switching to the popping mode. Here is pop, and here also pop, and then this is the going to the acceptance state. So this is the way how you can make a you can call it as a transition diagram for what? For an equal number of A's and B's. Let's consider this example. A 2 times A 2 times B. The stack is empty with only Z 0. First of all, we will read A. When we will read A, we will be here. This transition, a function will be executed and A will be pushed into the stack. In the second A, this will be executed. Again, another A will be pushed. So whatever will be pushed, after that, it will be removed. Then B, when it is B, this function will be executed. It will pop A. Then after that, this B, so as these are already done, if it is so here one A is left. Now this is your top. Here again it is B. So what will happen? This will be executed and khalas, it will be pop. As I told you, at the end of every string there is an empty symbol. So then if this is executed, here it is empty. So and the stack top is Z0. What you need to do is you need to just accept the string, because at the end the stack is empty, and also you reach to the final yani state. So when do we have to yani, change the state from Q0 to Q1? Whenever we need to make a diagram. If you are doing all push and then after that you need to do pop, then you have to. Here you was doing pop, then the acceptance state. That's why what we did, we actually moved to the new state. When we change the operation of the stack, suppose we are performing a series of push, will be in the same state, for example Q1. And if you want to perform pop, then you need to move from Q1 to Q2. Let's consider another example. Here you have a power n, b power m. For n, okay, here first of all, m will be equal to 1 or greater than 1. It means b will always be, yani start from 1, it can be 2 and 3. And the thing is, n is always yani greater than, a is always greater than b. So then a will be, maybe if b is 1, a will be 2. If b is 2, then a will be 3 times. Now, in this case, the diagram will be same. Only the thing is, what we need here is we need to yani, decide the number of times pop need to be performed. Yani here, every time, what you need to do is you need to perform pop even one more time. So for this diagram, for this case, if I need to make a diagram only for this, for example, what it will do that even this is the yani, the least string that you have. So what you will do, you will first do one time push, another time push, okay. So every time you will have plus one pop. So here you will do one pop, okay, and then because one time B will do yani one more time pop. So here one time yani this one as well as this one. So even for a yani single yani the smallest string, what you did, this is basically the PDA. Now here you will see inshallah later on, this is not only the final or the best representation to represent the PDA. In the next case we will see yani, that how we can also implement this by using a flow diagram. Now, for example, if we have another example which says that a power n, b power 2n for n is equal to 1 or n is greater than 1. So here it is very obvious what I need to do is I need to do one time push. I need to do one time push while 2 yani b 2n. So it will be basically what it will be. When you need to pop, you need to pop yani there are two b's. So in that case, what you have to do is that construct a PDA. Let's consider another example that accept a power n, b power 2n for the value of n is equal to 1 or greater than 1. In this case, what you have 1 time a, 2 times b. You have 2 times a, 4 times b. So in that case, here, if I need to define the logic, here you will do a push and you have two b's. So one b will ignore, no change. For another b, we will do a pop. So look, we have two a's. For one b, ignore, another b, pop. For then this b, ignore, this b, pop. So let's make a transition diagram for this one. So here, first of all, let's first draw it for using yani the least string, which is a, b, b. Inside the stack, you have just z0. So you wrote this as a function in order to define insert a. We don't need this for now. So here, as it is a, b, b, now a is push, it is done. For this b, what we did, we need to define something which is known as the no change. How we can define no change? You will see, because as this is push, this is no change, I need to move to another state. Currently, I am in Q0. The input is B. On the stack top, it is A. What you need to do is you need to go to Q1 and don't do anything. Keep the stack it is. It means the top will be still A. So here you can see that this is B comma A implies A, yani no change. However, when we have another B, it means that you are now in Q1. Okay, the input is B, the stack top is still A because you didn't make any change. What you need to do is, as this is a new, a new operation, you need to go to Q2, okay, and what you need to do is you need to do a pop. So this is basically the pop. Now, and then halas, here what you did at the end, as it is epsilon, go to the acceptance state. Now, if the string is yani 2 times A and 1, 2, 3, 4 times B. So first push, second push will be this one. Now, this one is no change. Here it will come, it will do the popping. Okay, this will be popped. Now, for this one, what we need to do is, I don't want to put a loop. What I will do, I will come yani back here. Okay, that again, no change. Okay, for this one, and then do the pop and khalas, do the acceptance. So this is basically a diagram for a power n to power n.